Everyone, in this video I want to walk through finding the inverse of a rational function. There's some messy algebra that comes up with this one and also some interesting domain stuff that comes up. So we will keep track along the way. Okay, so what is the domain of M is the very first thing we want to answer. Because M is a rational function, we're going to have to worry about division by 0. So the only thing I see that could give me a problem is t equals 3. I'll leave that out of my domain. So any t not equal to 3 is in the domain of M. Let's go ahead and work on finding M inverse. So we want to think about this as we have a function y equals 2t minus 2 over t minus 3. Let's switch our variables. Say t equals 2y minus 2 over y minus 3. And let's go ahead and solve for y. So switch your input and your output variables and then solve for whatever used to be your output variable. The solve step is what turns it into an inverse. To solve for y, I definitely want to get the y out of the bottom of the fraction, so I'm going to multiply both sides by y minus 3. I can go ahead and distribute on the left, so I will get a ty minus 3t. On the right, the y minus 3's wipe each other out, and I'm left with 2y minus 2. All right, the next thing I'm going to work on here is the fact that I have y's, not a very good pen here, on both sides of the equation. There we go. That is never a good thing when we're solving for y. So let's move the y's to the left, and I'm going to move any terms without y's to the right. You get to pick your side. It doesn't matter, but that's what I'm going to go for here. So if I'm moving y's to the right, I'm going to leave ty exactly where it is. And to get the 2y over there with it, I'm going to subtract 2y. These are attached by addition, subtraction, so that's how I need to separate them as well. The negative 3t does not have a y, so I'm going to go ahead and move it over to the right-hand side. It's attached by subtraction, so I need to add it. The minus 2 can just hang out. I want the minus 2 over there since it does not have a y. This actually turns into somewhat of a literal equation we're solving. We have more than one variable, and this step is very much like a tricky one we have to do in literal equations. If this was a 4y minus 2y, that's great. We would just combine and say that's 2y's, but since one of the coefficients is a t, we can't do that. Instead, we have to factor a y out. All right, and then last step, y is attached to all of this by multiplication. So I'm going to go ahead and divide. All right, and that's my inverse, and you can go ahead and call it M inverse at any point here. Okay, so for this function, we're also supposed to state its domain. We got another rational function, which means that we need to make sure the bottom does not equal 0. So this will have a domain restriction t equals 2. T does not equal 2. We can actually make a really nice conclusion out of this because the relationship between a function and its inverse is that the x's and the y's, or in this case the t's and the y's, are switched. Their domain and range will also be switched. So these rational functions, they're a little tricky for us. We haven't worked on graphing a rational function written in this form. We might not know what the range of this thing is just by looking at it. Hopefully by the end of the quarter we will, but we might not know right now. However, if we're looking at the rational function m and its inverse, we can say that the domain of m will be the range of m inverse, and the domain of m inverse will be the range of m. So this is kind of a cheat for us to figure out domain and range, but also this idea that the relationship between a function and its inverse is that the x's and y's are switched is really good in general. So this is just one way that we can see that that's happening. Another thing that's really good to do here, and I've already plugged them in, is to look at the graph of your function and its inverse. So you would want to hit your y equals and go ahead and type these two in. You can see I need parentheses around the top and the bottom. And then for good measure, I put y equals x in here as my third equation, and I will tell you why in just a second. Okay, so here they are. Let's see, I would like it to redraw. I don't know if I know how to do that. No, it's okay. What you should see is that if the relationship between a function and its inverse is that the x and y coordinates are switched, then the graph of the inverse will result if you take the graph of the function and flip it across y equals x. So when you're looking at the graph of a function and its inverse, if you put y equals x in there, you should be able to see that you have, with the two graphs, some symmetry across y equals x. So one of these two, let's see, the t does not equal 3. This top one right here is the function, and the one that starts out on the bottom and then switches to the top is the inverse. And those two are just reflections across y equals x of each other. So this is actually a pretty powerful check. If you're not sure you did your algebra right, you can look at the graphs, and the graphs should tell you, yes, these appear to be inverses, or no, these don't look anything like inverses. So checking graphs for every single one of these things is really great. Knowing what a relationship between the graphs of the two is going to be really helpful when we get into some trickier stuff. Okay, so we are supposed to do a little checking here, and this is kind of a two-part thing. One, you should be able to show me the algebra. So show me what happens when you plug m inverse of t back into m. Two, you should already know that if I answered the previous question correctly and they really are inverses, that when I compose, I better just get back t. So you know what the answer to this is, but you need to be able to do the work and verify it to see if you're right. Okay, so m inverse. M inverse is 3t minus 2 over t minus 2. And as I said, some of the algebra gets a little tricky, not just with the solving to find the inverse, but also with the checking. Function m takes whatever I give it, it builds a big old fraction. On the top, it puts 2 times my input. Let's go all the way down. Minus 2. And on the bottom, it puts my input minus 3. The very first thing I'm going to do is deal with the parentheses on the top. You can go right for clearing fractions, but I see people make mistakes, so I want to make sure we deal with this correctly. I'm going to multiply the 2 in. It only multiplies by the top of the fraction. This is a 2 over 1, not a 2 over 2. Which means, as of right now, I have m of m inverse of t equal to 6t minus 4 over t minus 2 minus 2, all divided by 3t minus 2 over t minus 2, subtract 3. Okay, so I've dealt with the parentheses. Next, I'd like to clear the fractions in fractions. So I would love to get rid of the t minus 2 in the top and the bottom. It's very convenient that they're the same. That means that I can just multiply top and bottom by t minus 2, and it should wipe those fractions out for me. Once again, if you need the reminder, you can put this over 1. We're going to distribute it into the top. And this is because a fraction bar is a grouping symbol. So if we multiply the top by t minus 2, that means both terms in the top need to get multiplied by t minus 2. When the fraction gets multiplied by the t minus 2, it will cancel. So that works out beautifully. I get a 6t minus 4. When the negative 2 gets multiplied by a t minus 2, nothing cancels. Do not forget to multiply the 2 by t minus 2. Since our goal is to cancel fractions, people generally don't forget to multiply the fractions, but they will forget that they also have to multiply the 2 and the 3. On the bottom, when I multiply the fraction by t minus 2, that cancels out again, and I'm left with a 3t minus 2. And then I have the minus 3 multiplied by the t minus 2. Nothing nice happens in terms of cancellation there. Almost done. Let's see if I can sneak this in. Okay, so I have on the top a 6t minus 4 minus 2t plus 4, distributing through those parentheses. On the bottom, I have a 3t minus 2 minus a 3t plus a 6. So some nice things happen. On the top, I have a negative 4 plus 4. That's going to drop out completely. On the bottom, I have a 3t minus 3t. So that will drop out completely, which leaves me with a 6t minus 2t, 4t on the top, and a negative 2 plus 6, 4 on the bottom. I then get to cancel out the 4s, and I'm left with just a t. This is what I was hoping for. It was definitely more work than when we're working with a cube root or a quadratic or any of the other ones. The algebra for checking rationals can be a little bit tricky, but you should still get to that t. If you don't, there's a problem. This question does have another part. We're supposed to state any domain restrictions. So as summary, what I figured out here is that m of m inverse of t, oops, that's where I wanted that, is equal to t, which is a good thing. If they're inverses, that should be true. It doesn't have to be true for all possible t values, just the t values that work for the inner function. So I did list that as something to know in this section, but it's really something to know from the last section. When you compose functions, if you want to figure out the domain restriction, you should look at what you ended up with. Y equals t doesn't have any domain restrictions. You should also check the inner function. The inner function, m inverse, is not defined for a t equal to 2. So we're going to say t should not equal 2. So no matter what t you pick, if you plug it into m inverse and then back into m, you should get what you started with unless you plug in 2, because if you plug in 2, m inverse will be undefined and you won't even make it through that first step. Okay, if you're feeling good about this, you don't have to watch me go through the other direction. It's really similar, but if you want some practice, it's messy algebra. So you could pause and try and work through this, and I will walk through the m inverse of m direction for this thing. Okay, so very similar idea. We're trying to plug m into m inverse. M of t is 2t minus 2 over t minus 3. If I plug that into m inverse, I'm going to get, let's see here, 3 times that whole fraction divided by our fraction minus 2. Okay. Again, I'm going to go ahead right away and deal with the parentheses so I don't mess up that. So I'm going to get a 6t minus 6 in the top over t minus 3. Okay. And then clearing fractions, I need to multiply top and bottom by t minus 3. Don't forget to distribute. So I'm going to get a 6t minus 6. So I have m inverse of m of t. 6t minus 6 minus 2 times t minus 3 all over, again, the fraction, the t minus 3 cancels, so 2t minus 2 minus 2 times t minus 3. Avoid the temptation to cross this out. T minus 3 is a factor of the last term, so is 2, but it's not a factor of the entire numerator. So unless you can factor it out of the entire top and bottom of the fraction, you can't cancel it. Instead, we're going to distribute and see if we can collect everything and then look for something that we could factor and cancel. Okay, so I have a 6t minus 6 minus 2t plus 6 over 2t minus 2 minus 2t plus 6. So on the top, there's a negative 6 plus 6. That will drop out. On the bottom, there's a 2t minus 2t. That will drop out. That leaves me with 6t minus 2t, which is 4t. Over negative 2 plus 6, which is 4. And if I cancel the 4, I'm left with plain old t, which is exactly what I was hoping to find. We're also supposed to state domain restrictions here. So this, again, it might look tricky, but all this is saying is that this new function we get when we compose M inverse with M is just y equals t. So this is function y equals t with a fancy looking name. The domain restrictions for this will come from looking at the equation, which has no domain restrictions, and also looking at the inner function, since this was a composition. The inner function had a domain restriction, t should not equal 3, which means this composition will always result in giving me back what I started with, as long as I don't start with a 3. If I start with a 3, function m of t is undefined, so I'm not ever going to get the chance to plug it back into M inverse and see what happens. Okay, that was a long one. Thanks for watching.